Okay, here we are. So, been a lot of discussion and complaints and everything else about how the hell do we determine what the pKa is in lab number 6. I blame myself. It's because we really haven't talked much about how to calculate pKa. We've talked a little bit about what a dissociation constant is in theory, but we haven't really dug down into how you would calculate it and how you would use it in this particular instance. And you're asked to calculate a pKa. So understandably, a lot of you have had some difficulties with it. I take full responsibility. Anyway, so this is from the lab, and we're looking at specifically acetic acid. And this is the reaction of acetic acid dissociating in water. Now, we know that if I have acetic acid, I put it in some water, I'm going to get some protons or hydrogen ions or hydronium ions, whoever you want to call them, and some acetate. So the problem here is this is a weak acid. If this was a strong acid, it would completely dissociate. And whatever concentration of acetic acid was in solution, I would get the same concentration of protons, H+, and that concentration of acetate ions. But we don't, because it's a weak acid. So what does that mean? What that means is this is a reversible reaction. And actually, it's the reverse reaction that is favored. So we get very little product formed. We get very little H+ and very little acetate formed when we dilute acetic acid in water and make vinegar. And how much product gets made is determined by the equilibrium constant. And we call the equilibrium constant K. K is loosely, not loosely, exactly, the concentration of the products of this reaction, and in this instance, H+ and acetic acid, divided by, acetate ion, sorry, divided by the concentration of acetic acid. And since K for acetic acid is low, we call this a Ka simply because it's an acid. That's where the A comes from. If it was a base, we would call it Kb for base. Since Ka is a low number, that means the concentration of H+ and the concentration of acetate are going to be small. And almost all of the acetic acid in solution is going to be in the form of the acetic acid unionized. So we'll just have acetic acid and very, very few ions produced. And what pKa means, this small p just refers to negative log. That's all it means. It means we take the log, the logarithm, the log 10 of the dissociation constant, Ka, and then we change it with a negative number. So since it's such a small number, and in acetic acid's case, Ka is 10 to the minus 4.75. That is the dissociation constant for acetic acid, 10 raised to the minus 4.75 power, meaning it's a little bit bigger than 10 to the minus 5, but it's not as big as 10 to the minus 4. So it's really, really small. So the log of this would be negative 4.75. And the negative log of it would be 4.75. That is the pKa of acetic acid. Okay. So let's look at the Henderson-Hasselbalch equation. Now, what this equation is a representation of what pH is at a particular point when we have a weak acid with its pKa, and what's the concentration of the conjugate base, which is, in our situation, this is acetic acid dissociating into H plus, an acetate ion. The conjugate base of acetic acid is the acetate ion. So here, if we can figure out what the concentration of the conjugate base is, or acetate ion, and calculate what the concentration is of undissociated acetic acid, we can figure out the pKa of this acid. Now, it also is the case that we can use this expression to sort of get a rough idea of what the pKa is, because at the point where acetate ion, the concentration of acetate ion and the concentration of acetic acid are the same, that means if we divide one by the other, we'll get 1. Now, what is the log of 1? The log of 1 is 10 to the 0. So the log is 0. What does that mean? Well, that means at this point, the pH equals the pKa minus 0. So in other words, when the concentration of acetate equals the concentration of acetic acid, at that point, the pH is equal to the pKa. So when does this happen? When do we get the concentration of acetate equaling the concentration of acetic acid? Well, at the beginning of the titration, there is no base added. We have not added any sodium hydroxide. And so the concentration of acetate ion should be really, really small, like really small. So here, we added no sodium acetate, sodium hydroxide. So our concentration of acetate should now be super, super small. And at the end, at the equivalence point, where we have exactly the concentration of hydroxide and the concentration of initial concentration of acetic acid, all of the acetic acid should be converted to acetate. So at this point, at the beginning, no acetate. At the equivalence point, all acetate. So halfway in between, we should have roughly the same concentration of acetate and acetic acid. Because at the beginning, it's 0. At the end, it's 1. Halfway between should be about 0.5. So each concentration should be the same, halfway in between. Well, if the titration is over at 25 mils, halfway in between is 12.5. What's the pH at 12.5? pH at 12.5 is a little less than 5. It's around 4.8 or so. So if the pH is 4.8, about halfway, that means the pKa of acetic acid is about 4.8. And we know that's true because the pKa of acetic acid is 4.75. That's pretty close to 4.8. Now, one of the problems with this is when we're doing a titration, we don't actually get to the equivalence point. We get to what's called the end point. And the end point is what we think is the equivalence point. It's an estimate of the equivalence point. So we only have an estimate of what the actual volume of sodium hydroxide is needed to actually titrate our acetic acid. It's a really close guess, but it's still only an estimate. So halfway is also an estimate. So what we need to do is to be actually able to figure out what the concentration of acetate is and what the concentration of acetic acid is. Basically, at any point, if we can calculate those concentrations and we know what the pH is, we can calculate the pKa. So let's do that. So here's table 3, the dreaded table 3. So this is from a titration that somebody else has done instead of using an indicator like phenolphthalein like we use that changes color, they actually have a pH meter, and a very a precise one apparently, that tells you what the pH is during the titration. So we can see that initially the pH is around 3.1, 3.2, what we would expect for acetic acid. Why would we expect that? Because a very small amount of protons are going to be released from acetic acid when we dissolve it in water, right? A very small amount. How much? Well, 10 to the minus 3.211. So around 10 to the minus 3, or 0.001 molar. That's about what the concentration of H plus is at the beginning. So that's a small amount of H plus. We don't know how much acetic acid there is. We're going to determine that by titrating it with sodium hydroxide. So they're going to be using a burette, and if you remember, a burette is that long, skinny glass tube that we put the sodium hydroxide in and measure it very accurately as it flows down through the stopcock into our flask where we're doing the titration. So how much sodium hydroxide is used? The final reading was 12.12 mils. The initial reading was 2.89 mils. If you take the difference, that would be the volume of sodium hydroxide used. The concentration of the sodium hydroxide is 0.1 molar, and the volume of the vinegar used is 21.05 milliliters. So we have a volume of base, we have a concentration of base, we have a volume of acid. Now all we need to do is calculate the concentration. That will tell us how much acetic acid was present at the beginning. Okay? So we need that information. So here, fairly straightforward to calculate the molarity of acetic acid. It's just concentration acid times concentration acid times volume acid equals concentration base volume base. It's a one-to-one relationship, so we can use this equation. Now, it gets a little trickier for the second sample, because now you have to do some more calculations. You have to figure out what the initial concentration of acetic acid is, and then it tells you how much base was used at the midpoint, like halfway through the titration. How much base was used at that point? We can figure out how many moles of base were used at that point. Then that'll tell us how many moles of acetate ion were produced. If we know how many moles of acetic acid there were at the beginning, and we know how much of that was converted to acetate ion halfway through, Then we can calculate both how much acetic acid is left, how much acetate is there, what's the ratio of acetate to acetic acid. That way we can figure out our pKa. So let's do that next. So here's the information we have. So let's write this down. So our concentration of sodium hydroxide, 0.1 molar. And I'll put another significant digit in there because we need to have at least 2 to do these calculations. What is the volume of sodium hydroxide used to do the entire titration? Well, that's the initial burette reading. That's the final burette reading. So the volume of hydroxide used final equals 17.31 mils. That's how much, so 20.31 minus 3. So this is the volume of hydroxide that was used to completely titrate the acetic acid. So the number of moles of base will be equal to the initial number of moles of acid. So let's figure out how many that was. So 17.31 mils is equal to 0.01731 liters, right? Because there's 1,000 mils in a liter. So if we divide this by 1,000, that's the number of liters we have. Now, to get the number of moles of hydroxide, we take the volume, 0.01731 liters, times 0.10 moles per liter. That's the concentration. That's the molarity. So how many moles is that? That is 0.01731 moles. So normally when we do titrations, we use very precise concentrations of our titrant, in this instance, base. We use like 1 molar or 0.1 molar or 0.001 molar to make our math easy. So this helps make the math a little easier. So that's the number of moles of hydroxide that was used. That also happens to be the number of moles of acetic acid at the beginning, right? Because we're titrating moles of acetic acid versus moles of base. And we get to the equivalence point when the moles of acid equal the moles of base. So if the moles of base is this much, at the end, that's because that's the same number of moles of acid that were there at the beginning. So we're halfway home. So that's the number of moles of acetic acid at the beginning of the titration. Okay. So let's put that aside. So that's our moles of acetic acid at the beginning. So let's figure out how many moles of acetate were produced halfway through. How do we figure that out? Well, the reaction is acetic acid plus hydroxide ion makes water and acetate ion. That's the forward reaction. And since we have a strong base, it goes forward. It does not go back. So look at the ratio. 1 mole of acetic acid plus 1 mole of hydroxide ion makes 1 mole of water and 1 mole of acetate ion. So halfway through, how much hydroxide have we used? Therefore, how much acetate ion have we produced? Well, let's look at what the numbers were at the midpoint. The number at the midpoint was 12.92 mils, minus the 3 mils that was the initial reading. And so our volume of hydroxide midway is 9.92 mils, or 0.00992 liters. Small amount. How many moles of hydroxide is that? Well, 0.00992 liters, times 0.1 moles per liter. That is the concentration of the hydroxide. So what do we get? How many moles is that? 0.000992 moles. Again, dealing with small numbers. So that's how many moles of hydroxide were used halfway through. That also tells us how many moles of acetate are present halfway through. That's the amount of acetate ion halfway through our titration. Okay, so let's review what we've got so far. What we have is our initial concentration, or initial amount of moles of acetic acid at the beginning. And that was, so moles of acetic acid was 0.001731. The number of moles of acetate halfway through were 0.000992. So, how many moles of acetic acid midway? So this is at the beginning, or initial. This is midway, and this is midway. How many moles of acetic acid were there midway? Well, if we start it with this much, and we've converted this much to acetate, then the difference must be how much acetic acid is left over. Start it with this. We've converted this much into acetate. The difference has to be the moles of acetic acid halfway. So what is the difference? The difference is 0.000739 moles. So I pretty much have everything I need to figure out what the pKa is. I know what the pH is halfway through. The midpoint pH reading is up here, and it is 4.895. So I know what the pH is. I know how many moles of acetate, and I know how many moles of acetic acid there are. Now, at this point, this is what the equation we're dealing with, right? pH equals pKa plus log concentration of acetate over concentration of acetic acid. So it's asking for the concentration of acetate and the concentration of acetic acid. So what we could do is take moles of acetate and divide them by the volume midway through. The volume midway through is the volume of vinegar that was there at the beginning, and that was 21.05 mils, plus the volume of base added halfway through, which is 9.92. But the thing is, we don't even need to calculate that. Why? Because the ratio of moles of acetate and moles of acetic acid is going to be exactly the same as the concentration of the acetic acid, or concentration of acetate divided by the concentration of acetic acid. Why is that? Because we're dividing both of these numbers of moles by the same number. We're dividing them both by the same volume. And so it really doesn't matter. If we have moles or moles per liter, as long as the volume is the same, top and bottom, we're going to get the same ratio. So we don't even have to do that. Makes our lives a little easier. And in table 3, basically, it just asks you what the number of moles are. Moles of sodium hydroxide dispensed, moles of acetate ion produced, moles of acetic acid left over. So you don't even need to calculate the concentration. You can just use the number of moles. So hooray for that. So let's set up our expression to do the final calculation, and then we'll be done. Okay, so what is, one last time, pH equals pKa plus log acetate ion divided by HA. And we're going to use moles instead of moles per liter because it'll give us the same thing. So what is the pH? 4.895, that's an 8, equals the pKa plus log, and here's where we put in our moles. So 0.000992, that was the number of moles of acetate, and we divide by the number of moles of acetic acid left midway, and that was 0.000739. So you can see they're not exactly the same. They're close, but they're not exactly the same. And so this expression, the plus log moles of acetate over moles of acetic acid, is going to be a fairly small number. It's going to be around 1. If it's dramatically different than 1, then you've probably done something wrong. It should be fairly close to 1. And in this instance, this ratio is 1.3424. So I go to my scientific calculator, or I go to my website that I showed you, and I plug in what is log of 1.3424, and it spits out that number is 1279. So it's a 9. So it's a small number, and it should be. It should be pretty close to 0. It should be slightly, it'll be either slightly positive or slightly negative, but it's going to be a small number. So now we have all the information we need, because now all we need to do is subtract 0.1279 from both sides of the equation, right? And that will leave us with pKa. So let's do that. So when we do that, we get 4.767 equals pKa. And we round it to the 3 digits, and we get 4.77. It's the pKa of acetic acid. What's the actual pKa of acetic acid? You should remember, the actual pKa is 4.75. So you can see we're really close. So you should get something fairly close to that. So that's how you do it. I've done it for vinegar sample 2. You do it for vinegar sample 3. All right. I hope this was helpful. And thanks for the people who said they were having a really hard time with it. That helps me figure out what I need to do better. And I didn't explain this terribly well the first time. Hopefully I've explained it a little bit better now. So good luck. Have a great weekend. All right. Bye-bye.